Welcome to The Explainer. Today, we're going to decode the hidden language of the web. I'm talking about those silent conversations that are happening every single time you click a link, log into a site, or even just load a page. So, when you type in a web address, you probably think of it as just, well, a location, right? But it's so much more than that. It's actually part of this really complex back-and-forth conversation happening between your browser and a server. It's a whole series of requests and instructions. And just like any conversation, it can be, well, twisted. Today, we're going to dive into 3 different ways that attackers can manipulate this digital dialogue. We're going to see how they can actually break into web applications, and we'll start with something surprisingly simple and work our way up to the really sophisticated stuff. All right, so let's get right into it. Our first vulnerability is probably the most straightforward one you'll see. I want you to picture this. You have a key to your hotel room, right? But then, just for kicks, you try it on the door next to yours. And it opens. That, in a nutshell, is what we call an insecure direct object reference, or IDOR for short. So how does this even happen? Well, it's when a website does a pretty good job of checking that you're logged in, but then it completely forgets to check what you're actually allowed to see. It's like the bouncer at a club checks your ID to see if you're old enough, but doesn't check if your name is on the VIP list. Now, what's really wild here is just how simple the attack is. Seriously, an attacker logs in, they find a URL that has some kind of ID number in it, and then they just change the number. That's literally it. And that simplicity, that's what makes it so common and, honestly, so dangerous. And this slide just lays it all out perfectly. You see the normal request here for account ID 1234. The attacker, who is user 1234, simply goes up to the address bar and changes that 4 to a 3. Boom. If the server isn't doing its due diligence in checking permissions, it just happily hands over account 1233's private data. A single-digit change. That's all it takes. Okay, so that was IDOR. Let's move on to our next vulnerability, which kind of builds on this idea. But now we're not just swapping out a value. No. This time, we're adding something totally new into the conversation, specifically to confuse the system. This is an attack called HTTP parameter pollution, or HPP. Think of it like this. It's like you're sneaking an extra confusing instruction right into the middle of a sentence just to see if the person you're talking to gets tripped up. The attacker is essentially hiding a brand new command inside an existing one, and if the server isn't paying close attention, it might just execute that hidden command. So let's use an example. Imagine a super simple online poll. You've got a clear choice, right? 2 candidates, Mr. White and Mrs. Green. Each link is designed to send a nice, clean, unambiguous vote to the server. So far, so good. Everything looks totally normal. But here comes the attacker. Let's say they're a supporter of Mrs. Green. They craft a special, malicious link. What they do is they pollute the URL by injecting a hidden vote for their candidate. They pull this off by using these encoded characters. You can see %26 here, which is just a fancy way of writing an ampersand, or the and sign. This little trick lets them sneak a second command into a part of the URL where the server just isn't expecting to see one. Now, here's the sneaky part. When an unsuspecting victim clicks on the attacker's link, the web page they see looks completely normal. Nothing seems wrong. But behind the scenes, that hidden vote for Mrs. Green has been injected into both voting links on the page. So even if the victim clicks vote for Mr. White, their browser is tricked into sending a vote for Mrs. Green, too. Okay, and here's the real kicker. Different web technologies handle this situation, having 2 identical commands in totally different ways. The server in our voting example, a JSP server, has a simple rule. It only pays attention to the first candidate instruction it sees. And since the attacker's hitting vote for Mrs. Green was injected at the beginning, the victim's actual vote for Mr. White gets completely ignored. The attacker wins. And look, this isn't just some obscure theoretical thing. A huge study looked at over 5,000 popular websites and found that nearly 1,500 of them, that's almost 30%, were vulnerable to these HTTP attacks. And we're not talking about small blogs here. We're talking about major e-commerce platforms, social networks, financial sites, places where this kind of attack could be used to manipulate product reviews, mess with transaction details, or even bypass security checks. All right, time for our final and definitely most complex vulnerability. We're leveling up here. We're moving beyond simple little parameters, and we're going to talk about attacks on the very digital passports that you use to log into countless services, everything from your work email to your cloud accounts. So we're talking about something called SAML. You might not have heard the name, but you've almost certainly used it. SAML is basically the magic behind single sign-on. You know, when you use your company login to access a bunch of different websites, that's SAML. It's a standard that lets a trusted source, like your company's IT department, issue a signed digital statement, that passport, that basically tells another website, hey, we've checked this person out. They're legit. Let them in. The security of this whole setup hinges entirely on that one digital signature. It's everything. But as researchers have pointed out, this can create a really deceptive illusion of safety. We see that signature, we see that stamp of approval, and we automatically feel more secure than maybe we ought to be.
The attack is called XML Signature Wrapping, or XSW, and it works by exploiting a really critical gap in the process. See, it fools the system because the part of the application that checks the digital signature is often separate from the part that actually reads the user's information. So you have one part saying, yep, this passport signature looks totally valid, while another part gets tricked into reading a completely different fake page of the passport.
So in essence, the system sees a valid signature on the outside of the digital envelope. It checks it, confirms it's legit, and gives a thumbs up. But then it gets completely fooled into reading a fake letter that the attacker has slipped inside that very same envelope. The signature itself is totally valid, but it's not for the data that the application actually ends up using. That's the trick. Okay, so we've just walked through 3 really different kinds of attacks, right? We had swapping a simple ID, we had polluting a URL parameter, and we had wrapping a digital signature. But for all their differences, they all point back to one single critical weakness. What's the common thread? It's a failure to be deeply, deeply skeptical of anything that comes from the user. It doesn't matter if it's a simple ID number in a URL, a bunch of parameters, or a complex document like a SAML assertion. The root cause is always the same, trusting input from the user's browser way too much. So what's the takeaway from all this? How do we defend the digital door? Well, it really comes down to a few core principles. It is not enough to just check if a user is logged in. You have to check what they are authorized to do every single time. It's about using complex, unguessable IDs instead of simple numbers. It's about being paranoid and validating all user input. And for stuff like SAML, it's about making absolutely 100% sure that the data you're using is the exact data that was signed. You know, this hidden language of the web, it's incredibly powerful. And understanding how it can be manipulated, how these conversations can be twisted, that is the first, most crucial step. It's what allows us to demand, and more importantly, to build a much more secure digital world for all of us.